Curvilinear coordinate systems 10. A tokamak fusion device has a geometry that takes the shape of a donut or torus. Calculations for such a device are sometimes done with the toroidal coordinates shown in the figure below, r, theta, the angle with respect to the xy plane, and phi, the angle with respect to the x-axis on the xy plane. Z-axis is the major axis, minor axis is this circle, defined by this circle. The major axis of the device is a vertical straight line that forms the toroidal axis of symmetry. The minor axis is a circle of fixed radius capital R0 that passes through the center of the donut. The position of a point is described by the coordinates r, theta, and phi. The coordinates r and theta are similar to a two-dimensional polar system aligned perpendicular to the minor axis. The coordinate phi measures the angular position along the minor axis. So in part A, we made a sketch of the basis vectors. We found that this forms a right-hand coordinate system, right-handed system. We have the transformation equations and the scale factors. Now we're doing part D. Write expressions for the displacement vector dr, a differential surface area d sigma, and the differential volume d tau in this system. First of all, we have to obtain the differential displacement dr. And we know that dr is partial derivative of r with respect to r dr plus partial derivative of the position vector with respect to the angle theta d theta and the partial derivative of the position vector r with respect to the angle phi d phi. So we have to basically look at all the coordinates and take the derivatives with respect to them individually. Now del position vector del r is basically the magnitude h sub r multiplied by the unit vector er hat dr. And then we have del r del theta, which is the scale factor h theta e theta hat d theta. And then we have h phi e phi hat d phi. So this is what we need to write down. Since we already know the scale factors, we can easily do this. This differential displacement vector dr. Remember that the scale factor hr we found previously was 1. So this is simply equal to dr er hat. And the scale factor theta that we have found was r. So it is r d theta e theta hat. And the scale factor we found for phi was r cos theta. So it is plus r cosine theta d phi e phi hat. So this is our answer for the displacement vector. Now, as for the area vectors, d sigma 1, remember that r, theta, and phi form a right-handed coordinate system. This will be equal to plus or minus hr h theta, which is r HR was 1, so H theta is R. R dr d theta, and this is in the direction ER hat cross product with E theta hat. So it is a HR H theta dr d theta. So HR dr H theta d theta, in other words, ER hat cross with E theta hat. The sigma 2 is now we're going to theta and phi plus or minus depending on the geometry. Now we have H theta and H phi. H theta was R, H phi was R cosine theta. So it's R square cosine theta, d theta, d phi, and then we have E theta hat cross with E phi hat. And the sigma 3 is now we're going to phi and R. So plus or minus H phi was R cosine theta, but HR was 1. So it's R cosine theta, dr d phi, E phi hat cross product with ER hat. So it must be perpendicular to both of these vectors. Now this tells me that the sigma 1 is, because R theta and phi form a right-handed coordinate system, ER hat cross E theta hat is E phi hat. So this is plus or minus R dr d theta E phi hat. And for the sigma 2, we have plus or minus R square cosine theta d theta d phi. Now R theta phi, so theta E theta hat cross E phi hat is ER hat. And for the sigma 3, we have plus or minus R cosine theta dr d phi E theta hat. So plus sign or minus sign depends on our geometry here. The area vector must be pointing perpendicularly outward from the enclosed volume. So that's basically our convention. Now, as for the volume element, d tau, we have HR1, H theta R, H phi R cosine theta, so it's R square cosine theta, dr d theta and d phi. This is how we write our differential volume element. Okay, so in this part we were asked to find the differential displacement dr. That means we have to take partial derivatives with respect to all the variables and multiply them with the differential changes, corresponding differential changes in those variables. So del r, del position vector, del r dr, del position vector, del theta d theta, del position vector, del phi d phi. And remember that the magnitude of this is the scale factor, and this vector divided by the scale factor gives us the unit vector. So this is simply HR ER hat dr, this is H theta E theta hat d theta, and this is H phi E phi hat d phi. So we substitute our scale factors to get the final answer. For the area vectors, the area vector defined by ER hat and E theta hat, that's perpendicular to both of these unit vectors, we have to calculate HR dr, H theta d theta. For theta hat and phi hat, H theta and H phi, d theta d phi, and for E phi hat and ER hat, we have to consider H phi and HR. H phi was r cosine theta, remember HR is 1 and H theta is r. So substituting this and noting that this was shown to be a right-handed coordinate system, we can write ER hat cross E theta hat is E phi hat, and then similarly ER hat and E theta hat here. And finally, for the volume differential volume element, we have to write HR dr, H theta d theta, H phi d phi, and that's the product of all of the scale factors r squared cosine theta dr d theta d phi.